Hey there. There's this incredible mathematical tool that can look at a super complex, kind of chaotic digital system and just turn it into a simple algebra problem. It sounds like magic, but it's real. It's called the Z-transform, and today we're going to decode it together. All right, let's jump right in.
So here's the plan. First, we'll see why the classic Fourier transform just couldn't cut it for some problems. Then, and this is the cool part, we'll see how to draw a literal map of a system's stability using something called a pole zero plot. After that, we'll connect all this abstract stuff back to real-world frequencies. And finally, we're going to put it all to work and solve an equation that looks pretty much impossible at first glance.
All right, so let's kick things off at the beginning. For a long time, if you were analyzing signals, the Fourier transform was your go-to. It was the king. But every king has his limits, and that's exactly where our story starts.
Right, so the discrete time Fourier transform, or the DTFT, is kind of like a high-performance race car. On a perfectly smooth, predictable track, it's amazing. But what happens when that track gets rough? What if a signal, say, grows over time, instead of fading away? Well, the DTFT just spins out. It can't handle it. This is where the Z-transform rolls in. It's like the all-terrain vehicle of signal processing, built for any kind of signal you can throw at it.
And here it is, the hero of our story, the Z-transform. Now that equation might look a little familiar, but trust me, that little z in there, that changes everything. It's like we've added a whole new dimension to our analysis, one that lets us explore a huge universe of signals that were totally off limits before, especially the unstable ones.
The best way to think about this is to imagine the Z-transform as a whole globe. The old DTFT, that was like being stuck on one single line of latitude, the equator. Yeah, you get a view, but it's just a tiny slice of the whole picture. The Z-transform lets us explore the entire globe, the whole complex Z-plane. It gives us the complete story of a system's behavior, whether it's stable, unstable, you name it.
Now, there is a catch. Of course there is. For the Z-transform to actually work, that big infinite sum in the formula has to add up to a finite number. It has to converge. So the set of all the z-values that make this happen is called the region of convergence, or ROC. And here's the deal. A z-transform without its ROC is basically useless. It's like having a map with no compass. You have the picture but no idea what it means.
Okay, enough theory for a minute. Let's see this thing in action. In this next part, we're going to see how all this abstract math creates a visual tool so powerful, it can tell you pretty much everything you need to know about a system, just by looking at it. This is what we're talking about, the pole zero plot. Seriously, this thing is like a system's fingerprint. It's unique DNA. It's a map. The little circles, the zeros, are where the system's output goes to nothing. But the x's, those are the poles. Those are the critical points where the system's output could literally explode to infinity. And the unique pattern of these poles and zeros tells us the system's complete identity.
Now here's the most beautiful part. The rules for reading this map are incredibly simple. For a causal system, if all of its poles, all those x's, are inside the unit circle on our map, the system is stable, period. If you find a pole sitting right on the circle, it's what we call marginally stable. It's teetering on the edge. But if even one single pole is outside that unit circle, the system is unstable. It's going to blow up. It's really that straightforward.
And get this, all of that powerful, deep analysis we just talked about can be done with one single line of code. Yep, with a tool like MATLAB, you just type this in and boom, it generates the map for you. You can instantly see if your system is stable or not. It's basically like having a crystal ball for digital systems.
So we have this incredible map of our system's behavior in the Z domain. But how do we use that to predict what it'll actually do in the real world, when it sees different frequencies? That's the bridge we're going to cross next. It's actually way simpler than you might think. Remember our globe analogy? Getting the frequency response is basically like taking a walk right along the globe's equator. That's the unit circle. Every point on that circle corresponds to a specific frequency. So you just take your system function, h of z, and you plug in that special value for z. What you get out is the system's response for that one specific frequency. Do that for the whole circle, and you've got the full frequency response.
And as you might have guessed, there's a powerful shortcut for this too. The freq_z command in MATLAB is basically a super calculator for this whole process. It does all that heavy lifting for you, instantly giving you a complete plot of how your system reacts to different frequencies. This is where all the theory really hits the road.
And now for the grand finale.
We're going to see how the Z-transform can take a problem that is an absolute nightmare to solve in the time domain and turn it into, well, a walk in the park. So, this is our beast. It's called a difference equation. See how the output y of n depends on its own past values, like y of n minus 1? That makes it recursive, and trying to solve this thing directly is like trying to untangle a massive, knotted ball of yarn in the dark. But with the Z-transform, we have the perfect tool to just snip right through the knots. This is where the real magic happens. It's like alchemy. The Z-transform takes this complicated mess of a difference equation and turns it into a simple algebraic equation. All those tricky time delays like yn minus 1 just become simple multiplications by z. It takes a problem that feels like it needs calculus and turns it into something you could probably solve in high school algebra. It's incredible.
So at the end of the day, what's the big takeaway? The Z-transform is so much more than just another math tool. It's a whole new perspective. It lets us step out of the messy, complicated world of time and into the clean, elegant world of the Z-domain, where problems that seemed impossible suddenly become solvable.
And that leaves us with a final, really fascinating thought. We've seen how the Z-transform gives us this simple map to understand the hidden world of digital systems. So it makes you wonder, what if we could create similar maps for other complex systems out there? You know, things like the stock market, or weather patterns, or even the human brain. What secrets could we unlock then?